Now that we have derived the approximate distribution for root n beta hat minus beta, where this distribution is available from the data, is observable because v hat can be computed from the data. Now that we have this information, we can do stuff with it. What can we do with it? First of all, we can evaluate estimation accuracy. Now to evaluate estimation accuracy, notice that root n beta hat minus beta is approximately normal with mean zero variance v hat. That implies, that means beta hat minus beta, which is this random vector divided by root n, is approximately normal with mean zero and variance v hat divided by n. Now, suppose we want to evaluate the estimation accuracy of the jth coefficient, the j slope coefficient, which is beta j hat. So for beta j hat, the approximate variance will be v hat jj divided by n, right? So remember this beta hat minus beta is the vector composed of the intercept beta 0 hat minus beta 0, beta 1 hat minus beta 1, to beta k hat minus beta k. And the variance-covariance matrix of this is composed of the variances of each one of these elements and the covariances between the pairs. So on the diagonal, on the main diagonal of the approximate variance-covariance matrix, we should have the approximate variance of each of these terms. So therefore, if we take the j plus 1 element on the main diagonal of the matrix, then v hat jj divided by n will be the approximate variance for beta hat j minus beta j. So v hat jj divided by n will be the approximate variance of beta hat j. And that is a measure of how accurate beta hat j is as an estimator for beta j. Just like before the midterm, when we were estimating the population expectation using sample mean, that sample mean has an approximate variance as well. And just like there, we usually use the square root of the approximate variance to evaluate the accuracy. The square root has a name, which is the standard error, which is called the standard error of the estimator. As we learned before the midterm, we know that there can be different standard errors for beta hat depending on which approximate variance formula we use for the estimator. Using this particular V variance estimator defined here, using this particular variance estimator, we can calculate this approximate standard deviation for beta hat, and that is a standard error for beta hat. That standard error is the robust standard error in Stata. The robust standard error that Stata produces. That is called the robust standard error. And you might wonder what the robustness mean. The robustness means that it is valid, it is consistent without extra assumption beyond our A1 to A4. Of course, there are, that you might imagine, there are other standard error formulas. There are other standard errors for the same estimator, which require stronger assumptions. And this one doesn't require stronger assumption. Now, using this approximate distribution for beta hat, we can answer the following question. For example, we can answer, what is the probability that beta hat makes an error no larger than C for some given positive number C? We can approximate that probability by probability that this normal distribution is less than or equal to C in absolute value. We can do that is because this is the approximate distribution for beta hat minus beta j hat minus beta j, which is the estimation error. So because that is the approximate value for the probability that the estimation error is less than or equal to this tolerance C. And how do you calculate this probability? Well, clearly because this is normal, we want to first turn the left-hand side into a standard normal. To turn that into a standard normal, we divide it by the standard deviation of that distribution. Of course, we need to divide that on both sides. So on the right-hand side, you should have C divided by the standard error of beta j hat, which is the standard deviation for this normal distribution. So that is the probability of a standard normal distribution falls inside these 2 points, where this is C divided by this standard error, and this is the minus C divided by the same thing. So the probability that the standard normal is in this part, is between these 2 points in this interval, is 1 minus the probability that it's the standard normal is beyond these 2 points, or that's 1 minus the 2 tail probabilities. In other words, that equals 1 minus the 2 tail probabilities, but because of the symmetry of the standard normal distribution, the 2 tail probability is equals 2 times 1 of the tail probability. So that should be 1, 2 times this, 2 times the probability that the standard normal is beyond this point. But the probability that standard normal is beyond this point equals 1 minus the probability that it's not beyond this point. So that's 1 minus the CDF, standard normal CDF, of C divided by this standard error. All right, so that is this probability. Now, this can be calculated from the data because everything here is available from the data. Now let's consider a numerical example where the standard error of beta hat j is 0.1. So this whole thing, that's the standard error, that is 0.1. And C is 0.2. So the probability that beta j hat makes an error no greater than 0.2 in this case will be 1 minus 2 times 1 minus CDF, standard normal CDF, times 0.2 divided by 0.1. Or in other words, that's 95.45%. All right, so another question that we can answer is, in order to achieve a desired accuracy, how much data do we need? To answer this question, we want to first realize that V hat is a consistent estimator for V. And V is something that only depends on the population. It doesn't depend on the sample size. So this is defined only by the population distribution. It doesn't vary with the sample size. So V doesn't change with sample size. On the other hand, V hat converges to V in probability. Therefore, for large samples, if the sample size is large enough, V hat is going to be quite close to V. That is, V hat stabilizes around V, which means V hat is not going to change much with the sample size. So V hat doesn't change much with the sample size. How does the standard error of the estimator change with the sample size then? Then it changes with the sample size, mainly because of this n here. So that means standard error of the estimator varies with the sample size approximately inversely. So it varies approximately inversely with the square root of the sample size. For example, if you want standard error to be reduced by half, then you want square root n to increase to double. Or in other words, you want n to quadruple. Now let's consider a numerical example. Suppose based on the sample size 500, we found that beta hat j has a standard error 0.1. That's the same. So that's the same numerical value that we used in the calculation we just did. Suppose that came from the sample size 500. Based on this standard error, we calculated that the probability that the estimator is no more than 0.2 away from the true value is 95.45%. Suppose I like the probability 95.45%. That is a good probability. That's very high. But I would like the estimator to make an error no larger than 0.05 with this probability. That is, my tolerance is not as big as 0.2 before, but instead my tolerance is only 0.05. That's, I want the tolerance to reduce to 1/4 as before. Then what's the new sample size that I need? To figure out the new sample size that we need, notice that we want the probability to be the same. The probability in the calculation of this probability, only one quantity is everything reduced to one quantity, which is the tolerance divided by the standard error. Tolerance divided by standard error, if that ratio is 2, then the probability is 95.45. So in the new situation, we still want the tolerance divided by standard error to be 2. Tolerance now is smaller, is 1/4 as before. Therefore, standard error should also be 1/4 of what it was. Standard error, how to make sure that the standard error is 1/4 of what it was? Well, you would want square root n to be 4 times as large, or n to be 16 times as large. So you want the new sample size to be 16 times as large, which would be 16 times 500. That would be 8,000. So that's how you determine the sample size to achieve an error probability that you want for a given tolerance. What else can we do with asymptotic distribution? There are some things that we have done before, like building confidence interval for each of the parameter. Let's say we want to build a confidence interval for beta j. then based on this approximate distribution, we can use this confidence interval. That's beta hat j plus minus the z-score times the standard error. The z-score is the 1 minus alpha over 2 quantile of the standard normal distribution. So this interval estimator should approximately cover the true value of beta j with probability 1 minus alpha. And ex ante, it has this coverage probability, and ex post, once you plug in the sample value of beta hat, sample realization of beta hat j, and the standard error, you're going to get a realization of this confidence interval. So that's how you construct the confidence interval. The formula is not so different from when we did the confidence interval for the population expectation before the midterm. Now that's the confidence interval. We can also test hypotheses. For example, we can test a single hypothesis like H naught beta j equals B for some given value B, like B equals 0 or B equals 1. So we can construct a test for beta j equals B. We can test that against two-sided alternatives. For example, H1 is the alternative hypothesis is beta j is not equal to B. In this case, you would want to use a test statistic that is big whenever the difference between these two values are big. So the difference between the estimator of beta j and B is big. So you want the absolute value of beta j hat minus B, and you want to standardize it using the standard error. Using the standard error. And we know by this, under the null hypothesis, B equals beta j, therefore this divided by its standard error is approximately standard normal. Therefore, that means we should use the critical value that is z alpha over 2, or 1 minus alpha quantile of the absolute value of the standard normal, okay, of the null asymptotic distribution of this. So the test as we have done before can be denoted by this phi n of significance level alpha is reject the null rejection if t is bigger than z alpha over 2. Or equivalently, the rejection rule is this. Reject H naught if the difference between beta hat and the hypothetical value for beta j is bigger than z alpha over 2 times the standard error of beta hat. So that's a two-sided large sample t-test. Clearly, you can also do one-sided t-test. That's when your alternative hypothesis is beta j greater than B. It's a one-sided alternative. In that case, you only reject the null when the estimator is much bigger than B. You do not reject when it's smaller than B. So you reject it when it's bigger than B by the one-sided z-score times the standard error. So that's the one-sided large sample t-test. Now with the two-sided large sample t-test, we can actually define a concept that's called the statistical significance of a regression coefficient. So the coefficient beta j is said to be statistically significant based on your given sample, if the absolute value of beta j hat, the estimator, is greater than the two-sided z-score times the standard error. Or in other words, beta j is said to be statistically significant based on the data if the two-sided large sample t-test for this h0 rejects the null hypothesis. All right, so in the next segment, we'll talk about something new that we can do.